Good day to my lecturer. I am Rivya Darshini with the metric number 24055025. Today, I am presenting my project for Sit3018 Non-Parametric Statistics. My study covers a graphical evaluation of social maturity profiles in mentally deficient children using the two-sample KS test via the pie chart method. This project analyzes historical psychometric data from Glosky and Vygotsky's 1964 study on children in a speech therapy program. Our core objective is to determine if children with early histories of aphasia exhibit different social maturity profiles compared to children without aphasia. We are testing this at a 5% significance level. Methodologically, we use the geometric pie chart method to visually assess differences across the whole distribution curve. Before starting, I audited the raw data and found a clear discrepancy in the literature. The original text states that the study split 42 children evenly into two groups of 21. However, a manual count of the scores provided in Table 1 shows that the aphasic group X has exactly 20 scores, while the group without aphasia, Y, has 21. To maintain absolute mathematical precision, this analysis proceeds with the true sample sizes of n equal to 20 and m equal to 21. Our null hypothesis states that the social quotient score distributions for both populations are identical, meaning there is no profile difference. The alternative hypothesis, on the other hand, states that the two distribution curves are different. Now, this test relies on two core assumptions. First, that the two clinical samples are mutually independent and unpaired. And second, that the data scale is at least ordinal. Since social quotient score have a natural numeric order, these two conditions are met. The traditional KS test assumes continuous data where exact ties should theoretically not happen. However, because clinical data relies on rounded whole numbers, ties do occur. To handle this without introducing directional bias, the pie chart applies strict geometric rules. When a tie happens between the two groups, the path moves exactly 1 unit diagonally, meaning 1 unit to the right and 1 unit up at the same time. Ties within the same group are simply plotted sequentially along that specific group's axis. This slide shows the summary of our audit combined sample data. We pulled all 41 observations together and arranged them from the lowest score of 16 to the highest score of 97. We then tracked the cumulative counts for Group X and Group Y at each step to compute our empirical distributions. Looking at the table, which will be in the report, we can easily see how our geometric steps are formed. For instance, score 16 starts our horizontal movement. Scores 20 and 24 represent consecutive ties between the groups, incrementing both X and Y. Then from score 25 to 30, we see a heavy run of Y group observations where X stays fixed at 3 while Y accumulates from 2 up to 6. If we calculate the absolute difference at every single row, the widest divergence between our two samples occur at a score of 61, showing an absolute difference of 0.183. Here is our finalized visual pie chart. The horizontal axis tracks the aphasic group up to 20 and the vertical axis tracks the control group of 21. The red line represents our reference diagonal of perfect baseline equality, while the blue line traces our actual data path. Moving from the origin, notice the sharp vertical wall on the left where the path shoots straight up from Y2 to Y6. This visually maps a heavy early cluster of control group scores. The widest vertical gap, where the blue line drifts furthest below the red diagonal, occurs right here at coordinate 1714, which corresponds to our score of 61. Now, let's review the arithmetic behind the maximum visual separation. The test statistic D is the largest vertical distance between our two sample functions. At our maximum divergence point of score 61, the empirical cumulative proportions are 17 out of 20, or 0.85 for the aphasic group X, and 14 out of 21, or 0.667 for the control group Y. Subtracting these values gives us our final calculated test statistic D of 0.183. Next, we determine our critical rejection boundary at the 5% significance level. By plugging our sample sizes of 20 and 21 into the large sample critical value formula right here, we find our critical threshold is 0.425. Our decision rule states that we will reject the null hypothesis only if our calculated sample difference D is greater than or equal to the critical value of 0.425. If it is less, we must fail to reject the null hypothesis. Comparing our results, our calculated D of 0.183 is much smaller than our critical threshold of 0.425. Therefore, we fail to reject the null hypothesis. Clinically, there is not enough evidence at the 5% significance level to say that the social quotient distributions of the two groups are different. Their social maturity profiles are broadly similar, and the minor variations we see on the graph are just due to normal random sampling variation. Now, to reflect on this methodology, using the graphical pair chart offers clear advantages over a purely arithmetic calculation. An arithmetic evaluation collapses our entire dataset into a single maximum value of 0.183, completely hiding how the rest of the scores behave. The pair chart, however, preserves the whole distribution shape and spread. It pinpoints exactly where deviations happen, showing us that our two clinical groups match nearly perfectly at the lower and upper developmental extremes, and that their variation is isolated strictly in the mid-range. It allows us to spot structural trends by tracking the direction of the steps over time. Now that concludes my presentation. Thank you very much for your time.